Hi guys, look, my apologies in advance for this one, the latest in the HSC Chemistry series on industrial chemistry. This is going to be slightly longer than usual. This is the first in the series on the equilibrium constant, and there's quite a lot of things to cover. So I've tried to split this up over a couple of videos, but unfortunately there's a fair bit to get through, so let's get into it. So the first thing, I guess, to talk about is that we've looked before at equilibrium systems where we have reactants forming products. And we know that depending on which state each of these species are in and what's happening to them, we can identify effects of changes in temperature and pressure on each of these systems. But what we want to do now is we want to start trying to quantify these, to actually put some values, some numerical values on each of these. So let's start to analyze these systems in a slightly different way. If we look at the reaction, then what we can expect is at the beginning, we have, say, 100% of each of our reactants and 0% of each of our products. So we have no products to begin with, and we start with 100%. As the reaction proceeds, the concentration of A and B both decrease. At the same time, the rate of the forward reaction decreases, and we can explain this using the particle model, because the particle model says that little particles will bang into each other, and the more often they do that, the more likely they are to react, and the more energy they have when they run into each other, the more likely they are to react. And that relates to things like numbers of collisions and also activation energy, which are concepts we looked at in the preliminary course. But as the number of particles decreases, then they don't bump into each other as often as they were, and so therefore the reaction rate starts to slow down. The reverse of that, of course, holds true for C and D. In C and D, as the reaction starts to proceed, their concentrations start to increase. And so the rate of the reverse reaction, which initially is 0, it's not happening at all, starts to increase as well. And we get the products reforming the reactants. Now, at some point, the rate of the forward reaction is equal to the rate of the reverse reaction, and that's what we've called equilibrium. So what are some of the important conditions? Well, the first thing is that the time that it takes for different species to reach equilibrium varies from one reaction to another. We can use a catalyst to speed up the rate of the reaction, but it does not affect the final concentrations. It's not going to change the position of equilibrium. And of course, one of the important things that we need to remember is equilibrium does not equal equal concentrations. While it's possible that an equilibrium situation, a system could actually reflect equal concentrations of reactants and products, it almost always doesn't. And most of the time we find that the concentrations of the reactants is greater or less than that of the products. So, a bit of a wordy definition, but one that I will walk you through in the next couple of videos, in fact. So at equilibrium, the ratio of the arithmetic product of the concentration of the substances on the right-hand side of the equation divided by the arithmetic product of the concentrations of substances on the left-hand side is a numerical constant called the equilibrium constant. Now that's pretty messy, so let's summarize it as pork. Pork means products divided over reactants equals K. Products over reactants equals K, and K is the equilibrium constant. So you'll find that K value is referred to a lot from now on, and the concentration of the products divided by the concentration of the reactants is equal to the value of K. So let's look at some examples of how we can calculate that. I guess firstly we need to be aware of the fact that if there's more than one product, we have to multiply the products, and if there is a coefficient well, if the coefficient in front of each species is not 1, then we must raise our concentration of that particular species to the power that's equivalent to that index. Now again, that probably doesn't make a lot of sense, so we probably need really to have a look at some examples. So the reactions that we've looked at previously, that one where we had A of A plus B of B in equilibrium with C of C and D of D would look like this. The concentrations of the products, so this is the products, is here, C raised to the power of little c, multiplied by D raised to the power of little d, so this is where these numbers are coming from, all divided by the concentration of A raised to the power of little a, multiplied by B raised to the power of little b. This is an expression for the equilibrium constant, and this is where these numbers have come from. So what does that mean? Well, there's a couple of important things, and I guess a couple of riders first of all. One of the things that's very important is that K is temperature dependent. If we change the temperature, we will change the equilibrium constant. So we need to remember this because we will find that most equilibrium constant calculations actually have a temperature specified for them, and that's the reason for that. But the only thing that can actually change the value of K is temperature. Once we can calculate a value of K, then we can use it to work out what would happen if we change the concentrations of any of the species in an equilibrium system, in a reversible reaction. So an expression for the value of K for this particular reaction would look like this. K is equal to products over reactants, which is equal to the concentration of NH3 raised to the power of 2 divided by the concentration of N2 multiplied by the concentration of H2, and again that is going to have to be raised to the power of 3. So that would be the equilibrium constant expression for the Haber process. And I've just scribbled over it, but you can read it there. So let's look at another example for a reaction and see if we can write down the equilibrium constant expression. So again, this time hydrogen gas plus iodine gas forming hydrogen iodide. So if we remember PORC, you may choose another acronym if you prefer, if that's not one you want to be remembering, but products, concentration of the products over the concentration of the reactants is equal to K. So therefore K is equal to HI raised to the power of 2 divided by concentration of H multiplied by concentration of I. How did you go? Thanks for watching.